Okay, so here's like kind of just a summary of who we've met so far in our development of calculus. We started with Zeno and Archimedes, kind of flirting with infinity over 2,000 years ago. And then we have this little bit of a dry spell for about, 16 or almost 2,000 years. And this guy named Isaac Newton and Gottfried Wilhelm Leibniz come around and invent this thing called calculus independently. That's what last week was about. And as sort of calculus developed, these players who we've learned about sort of made it a little bit more precise, a little bit more rigorous, a little bit more logically sound. It started with really just intuitive notions. And these players who we've met, Cauchy, the French mathematician, very staunch conservative, has amazing contributions to the logic of calculus, whereas Weierstrass kind of came later, mid-1800s, and officially cleaned it up. Fourier, the French mathematician, really a French physicist more than anything, messed with heat flow and said that continuity was no good, and Bolzano really emphasized, he didn't say continuity was no good. He said that there are a lot of physical phenomena that don't obey continuous functions, and we have or are not necessarily continuous, or certainly don't act continuous. And Bolzano says, yeah, I agree. Continuous functions, we need a much better definition of continuity. So here are the Avengers so far for our story of calculus, and we have two more to meet today. These guys are awesome. I'd say this first guy I'm going to introduce you to is one of my personal favorites. Let's say what's up to Leonard Euler. So Euler is widely regarded as the best mathematician of all time. So here he is, ladies and gents. If you want to say who's the best mathematician of all time, I would argue, most would agree it's Leonard Euler, just because of his intuition and his fervency to really expand the world of mathematics. This dude would not stop writing amazing works on mathematics. I'm pretty sure he's the most prolific mathematician of all time. In other words, the most mathematical results are attributed to this guy. And he's also kind of like, he seems like just like a stand-up family guy. He had cats. He had a huge family. He said that most of his life he was doing mathematics with cats in the room and children running around. So really love this guy. He was born in April 15th, 1707 in Switzerland. He was a student to another famous mathematician who hopefully we will meet at some point, Bernoulli. He worked across like tons of areas of mathematics and physics. Like I said, he's wildly prolific mathematician. Most of his career was in St. Petersburg and Berlin. He was tireless, systematic, generous, and just insanely productive. He also went blind like when he was in his 40s or something like this, and it truly did not stop him. In fact, I think he joked that he said with less vision that gave him more focus, less distractions everywhere because he has less sight. So what are his contributions to calculus specifically? He had contributions across mathematics. For instance, there was a famous question, the seven bridges of Königsberg. It asked this question: is there a way to cross all of these bridges only once? Okay, so like I just tried right there. Let's see if we zoom in here. He proved that it's impossible. It had something to do with graph theory. He actually developed graph theory. So if I were to zoom in. So the riddle is this: is there a way to cross all of these bridges only once? And let's see. Okay, so I'm crossing these guys only once. Going through here. Shoot, can't get back to this one. So I don't know, maybe like this. I don't think so. And you can play around with this game. The people of the day played around with it for a while, and people never found a solution. So Euler came along and said, well, yeah, it's because there is no solution, and here's why. And he developed all of graph theory to answer the question. It has to do with graphs. For instance, this can be simplified to look like this. This is what I call a graph. And the question can be simplified by observing this object right here. This is what I call a graph. And he developed this idea of like there's a degree of a graph, or excuse me, these are called vertices. These are called, so yeah, this is vertice, and these are called edges. And I'm honestly forgetting what he came up with, but it has something to do with, well, he had more notation, like this is a vertice, edge. And then he said like each vertex has some sort of degree, and that is the number of edges attached to it. So this vertice has has a degree of 3 because it has 3 edges. This vertice has a degree of 5. This vertice has a degree of 3, and this vertice has a degree of 3. And I think he had some sort of theorem where I think the vertices have to have degree or even degree, and it makes sense. If you enter a vertice, you have to leave it. That is the idea. If you go through, you don't want to get stuck anywhere. If it had odd degree, then you're definitely going to get stuck at that vertice. There's more theory, but that's not what this video is about. But anyways, beyond genius, this is the development of graph theory through the 7 bridges of Königsberg. But this class is not about graph theory, so who cares? Here's some of his writing. This is something to do with spherical geometry. Very pretty writing. I'm impressed with what this dude was able to do. In fact, the entire world was wildly impressed with what this guy was able to do. I think in this picture, he was already slightly blind. But what were his contributions to calculus in particular? He loved calculus. He was he was born when Isaac Newton was kind of on his way out. So he kind of played a huge role in the immediate development of calculus. He helped normalize and generalize things like the chain rule, which is something we just learned about. That's what this week is really about, applications of the chain rule. He saw calculus as an algebraic system. He clarified differentiation of transcendental functions. In fact, a famous function that he worked with all the time looks like this: y equals e to the x. And this is a famous function and wildly powerful function. This number right here is called Euler's constant. Or excuse me, Euler's number, I believe. Euler's constant is different. But yeah, Euler just had a huge role in expanding calculus beyond geometry and into symbolic analysis. He defined this thing, the exponential function, analytically, not just geometrically. He proved that this thing is its own derivative. He talked about this thing, logarithms, exponential growth, differential equations. He showed that exponential change is the simplest self-replicating rate of change. Huge contributions to mathematics. And much of the modern symbolism also, like for instance, functional notation, f of x, this is also contributed to him. He wrote over 800 papers and books. He could do insanely long calculations completely in his head because, well, he felt like he was forced to do that because he was blind after all. So he was just forced to do these insane complications or insane calculations in his head. And again, most of the notation that we use today in calculus traces back to Euler. Not only the notation, but literally just the results. So much mathematics is attributed to this guy. But who else developed calculus with us? Let's see. We have a woman mathematician, Maria Agnesi. She was born in Italy. This girl's mad genius as well. Could speak a ton of different languages. And she's mostly famous for being she's the author of one of the first calculus textbooks. Here's a picture of it right here. And wildly disciplined, super humble, devout and intellectually rigorous. Here's her development of a famous curve called the Witch of Agnesi, named after her. That curve came up in a previous video in this course. Mad smart woman. She focused on clarity, structure, and like sort of how to teach good mathematics. That was her goal. She wanted to tell people about this world of calculus that was recently developed by Isaac Newton. She presented these differentiation rules in a nice systematic way. So like things like the recent chain rule that we just developed, f of g prime of x. She had huge contributions to how this was taught. Times g prime of x, that's something we know. She really transitioned calculus from the world of research. Like she wanted it not to be only approachable by grad students. She wanted it to be approachable by the world. So she developed textbooks to really express how to differentiate, how to do calculus, why things are useful, things like this. She authored this. I'm not going to be able to say this, but this is one of the first modern calculus textbooks, and it is her authoring. So we learn calculus because of this framework and because of the first couple books that were developed, and it's from this girl right here, Maria Agnesi. She's so noble that after she wrote this textbook, she gave up mathematics completely, and she devoted her life to caring for the poor. Wildly impressive lady, super smart, super disciplined, changed. I look up to her because I try to be, a good teacher of mathematics, and she was one of the first and foremost good teachers of mathematics, in particular how just the immediate development of differentiation, which is what we were learning today. So she kind of set the framework for differentiation. To summarize, Euler showed how differentiation works across all functions, not just curves. Agnesi showed how to teach and organize these differentiation ideas clearly. Together, they really helped transform calculus into this universal language of change, which is what we are currently learning in this course together here. 2 new players have joined the sort of group of Avengers, and tune in next time for when I develop the timeline and we meet a few more.